Okay, so now we defined and saw how to compute the entropy of a distribution. Next, we're going to see how we can combine it with a reinforcement learning agent, how we can use this in RL, and why we should use it in RL. So we're going to use the entropy term, or to define the entropy over our policy, specifically a soft policy. Remember that a soft policy provides us with given a state from the environment, it provides us with a distribution over the actions, not a specific action like a hard policy, an argmax policy, but now we have a distribution over the actions where we hope that the best action will have the highest probability, right? Okay, so now we can define an entropy to our policy, and now we can require that our policy will be of higher entropy. Why should we do that? We'll see it in a second. But now we can change the objective, or change the way that we define pi star, our optimal policy, not just as maximizing the sum of rewards, or sum of expected rewards, right? And of course this can be discounted if we have a discount factor. Never mind. But we can now request or require that the policy that we are training returns the highest sum of rewards, but also is subject to be within some entropy bound. So we would like the entropy to be larger than some bound. We don't want our policy to collapse on a single action, but we would like it to be as random as possible, but still perform well, right? So we'd like to optimize performance subject to the entropy does not go below some value. We want to act as random as possible. Of course, we can use Lagrange methods to combine our constraint with our objective function and have a single objective function which is a linear combination of the sum of rewards or discounted rewards, again you can add that, plus some coefficient multiplied by the entropy term. And this is known as the maximum and max end RL objective. Maximum entropy RL objective, but in the literature you'll see it as max end. Okay, but it means the same. Why is it useful to do this? So it has several conceptual and practical advantages. The policy in this case is incentivized to explore more widely. That is a high entropy policy, while giving up on clearly unpromising avenues. Why? Because we're optimizing some combination of the rewards, so we would like it to go towards favorable outcomes, but also increase its randomness, random actuations, random control. The policy in this case, a high entropy policy, can capture multiple modes of near optimal behavior, and in many cases this is something that's of high value for us, specifically if the environment changes, or in cases where we do want to have a contingency plan, so it will allow us to know about all modes of optimality. Again, in many real applications that's important. Finally, in problem settings where multiple actions seems equally attractive, so that's not an advantage, this is just an outcome where in problem settings where multiple actions seems equally attractive, the policy will commit equal probability mass to those actions. Right, so this can help us avoid local convergence and to adapt more easily to new settings. And this is from the paper that presented A3C that we previously discussed. They say adding the entropy of the policy, right, the max end objective, improved exploration by discouraging premature convergence to suboptimal deterministic policies. This technique, so they also acknowledge that this technique was originally proposed in 1991 by Williams and Penn. Okay, so this leads us to the soft actor critique algorithm, which defines an off-policy actor critique which is an off-policy actor-critique algorithm that is based on the maximum entropy principle. It attempts to address two major challenges in model-free deep reinforcement learning. First of all, the high sample complexity, and secondly, the brittleness of two hyperparameters, right? So these are two things that we previously saw. Most RL algorithms require a lot of samples from the environment in order to improve the performance and eventually converge on good performance. And also, most of the algorithms are in danger of instability and divergence in learning. Right? They are very brittle, the performance is very brittle to the hyperparameters. If we don't set that correctly, in many cases we don't see learning at all, or learning divergence or learning collapse in some cases. Very unstable. So soft actor critique attempts to address that. Here the actor aims to simultaneously maximize the expected return and also the policy entropy. This is the max objective, as we discussed. That is, to succeed at the task while acting as randomly as possible, as we just saw. So an actor-critique architecture so the algorithm is composed of an actor-critique architecture with separate policy and value function networks. So we have two approximators, one for the Q network, Q values, and another for the policy that will provide us with the soft policy. Secondly, it performs, the soft actor critique is off policy. It does off-policy learning that enables us to reuse previously collected data for increased efficiency. Right? As long as we do off-policy learning, once we change our policy, we can still use previous transitions. Finally, it includes policy entropy maximization term to encourage stability and exploration. So as I said, soft actor critique is an off-policy actor critique training, performs off-policy actor critique training with a stochastic or soft actor, right, which takes the state and provides a distribution over the actions. So this is something that I said initially. Soft actor critique is not really an actor critique algorithm according to the classical definition, because the Q function is estimating the optimal Q values, Q star values, and not Q values for our current actor. So it doesn't criticize our actor technically, right? And also the actor does not directly affect the Q function except through the data distribution, right? We don't ask the actor we don't do Q propagations based on the actor's actions. So in that sense, it is considered an off-policy algorithm, but not exactly an actor critique algorithm. That's not really a critique in this case. But since it does so, it allows it to be off-policy, right? Not rely on specific transitions from a specific policy. Our objective function is the max end objective function, as we defined it previously, right? We would like to maximize some combination of the sum of the rewards plus the entropy term over all time steps. In this case, you can see alpha here that defines the linear combination between the entropy term and the rewards. Alpha is a temperature parameter that determines the relative importance of the entropy term versus the reward, and thus control the stochasticity of the optimal policy. Right? If you have a higher alpha, you'll have a more random policy. Right? Will act more randomly. If you have a low alpha, then eventually you will converge on a local optimal policy which maximizes the reward. And of course, alpha does not have to be static. Usually, we've seen this before, we like to start training by acting very random, explore the state space, and gradually we would like to converge on the true optimal policy. So it is very common to decay alpha over time. As learning progresses, we decay alpha towards 0, and once it is 0, then it's we are left with the conventional RL objective function of just maximizing the sum of rewards. Question?
In SAC, isn't it also common to tune alpha, not just degrade the value, to tune the value of alpha?
Oh,
yeah.
Yes. Okay, so when I say dynamic, yes, the alpha is dynamically adjusted, can be dynamically adjusted, right? You can take any value. You can decay towards 0, but in some cases you might want to increase it, right? What I'm saying is that you can play with it dynamically, and over time you probably want to decay towards 0, but we'll see a specific approach to dynamically adjust alpha that does decay over time in most cases, but it can increase in some cases, right? Yeah.
Could we add a similar entropy term like this to the stochastic approaches such as PPO and still see such advantages?
So we could, and many people do see advantages, so you might. The max end objective is not specifically tied to a single policy, right? You can say, well, my reward function, this is what I care about. So you can actually include an entropy term in your reward function, right? And then yes, you have practical max end objective that can define an MDP, and then you can use any RL methods, right?